working for the Coke company, and you are given the task that I need to minimize the cost of manufacturing of the Coke tin. Okay, so usually we know that it's a thin aluminum sheet which is actually used, and it's roughly in the cylindrical shape. So when I kind of say I will have to kind of go and manufacture, so if I typically think of a cylinder, so what is the most important varying thing when I kind of make a cylinder which will have to carry a Coke of 300 ml? Automatically the thing that will come to my mind is what should be ideally the radius and the height of this particular tin. So automatically that is the first thing for me to identify what are the associated design variables whenever I think of a problem. And the other thing which I will also need to understand is the objective function. Means what is going to drive this problem? What is the main objective behind this entire exercise? So as I did tell you, in this context, the main objective is to minimize the cost of manufacturing of this Coke tin. So we can easily write this also in some sense. So when you say minimizing the cost of construction, so using the concept of engineering drawing, when I open a cylinder, I'll be getting the bottom and top as assuming circles right now. And when I open the lateral surface, I will be getting a rectangle. So I can get the area of the surface area, lateral surface area of, okay, of the Coke tin with in addition. So which means I will get 2 pi r into h is what I will be getting the lateral surface area, and the top and bottom area is pi r square. So 2 pi r h plus 2 pi r square is what is the total surface area of making the tin. And if I multiply that with the cost of that aluminum sheet which I am going to have, and I will need to minimize that construction cost. So that is how I kind of frame a model for an objective function. And in many instances, what will actually happen is I will not necessarily limit myself only with respect to one objective. And in real life problems, you will always see multiple objectives are going to come. For those who are interested, you can always refer material. I will refer to this a little later when I tell this. And then the third important component is about constraints. So what do you mean by constraints? What are the necessary conditions that I will have to satisfy while I am going to minimize the cost of construction of the Coke tin, okay, or manufacturing of the Coke tin. So what did I say earlier? There is a Coke tin. I need to minimize the construction cost, and subject to this Coke tin going to have 300 ml of Coke. So which means, how do I kind of put this as a condition? I can always say that the volume of Coke tin is pi r square h, right? So that is going to be 300 ml, is going to be equal to 300. That is what is the condition that I will have to satisfy, and my radius and height should be a non-negative variable. So these are all some things if I keep in mind. This is what in brief is actually called as mathematical modeling, right? So usually when I try to solve such problems with some of the popular techniques, you will automatically see that you will be getting some very good solutions for such kind of real life problems. Now, when things go into a multi-objective thing, you will no longer have only one solution. You will always have a set of solutions which we will call as Pareto optimal friend. And then I leave it there and move on, because that in itself is a one semester course. Okay, just to briefly get you introduced to that particular topic. Now here, if you kind of see, once you formulate a mathematical model, there are so many methods available in literature for us to actually decide which are the most popular ones. So in today's time, I'm only giving you an instance, like whichever methods are going to emulate what is actually, or what are the usual nature inspired scenarios something like how we have evolved with time from our ancestors to how we are, or how typically these ants go in a particular line in search of food, and after some time you will see that they follow a path which actually is an optimal path, or you will see this is actually a swarm of birds. Okay, they go in search of food from season to season, and at some point after something, the path with the obstructions what they have is actually the optimal path. Or something like this is a firefly, this is a cuckoo bird. Each one has its own analogy in terms of how things are, like how lions hunt, how, and based upon that particular thing, you can actually see that the formulated mathematical models can actually be solved to actually arrive at the optimal solution, right? So they also have a lot of benefits. Maybe because of paucity of time, I'm going to skip this particular slide. Okay. And in all these particular things, I'm only going to give you some 2-3 instances of how beautifully these algorithms work. Like, more importantly, like in our school days or college days, wherever mathematics courses that we have learned to solve many problems, usually what we will always learn is there is one point that we start. Like, for example, I'll quickly give this instance. So if I will have to get the global optimum, we have learned in our calculus courses that I'll assume an initial point, and based on the slope of the curve, I'll try to keep exploring with multiple iterations and I'll arrive at the maximum point, say for example, right? So, and generally, the reaching the global optimum depends upon where you start. If you had started somewhere around this peak, you will end up here. If you had started a point randomly, assuming some point, you might end up here. But actually, we know that the global optimum is here, right? So all these nature instances that they kind of start, and then they have a selection process and a recombination and a mutation process by moving that point to a newer point by simply mimicking the nature's analogy with respect to many of the algorithms, whatever I briefly mentioned to you. And then they go through a rigorous selection process, and this happens iteration by iteration, and finally they will arrive at the optimal solution. This is what, in brief, these algorithms actually work. Just because of paucity of time, I'm only going to show you one video of how exactly this actually works. So if you see here, initially, there are points all over the search space. The actual point is here. This is where the actual global solution is there. They are all spreading, and iteration by iteration, they are all changing. Now, if you see that as the iterations keep increasing, all these points are climbing up the hill for the maximum point. And ultimately, these algorithms are going to be very, very powerful for us to solve any formulated mathematical model to ultimately arrive at the global optimal solution. This simple animation is a beautiful representation of how, without any hesitation, you can use all these algorithms, which we will kind of term this as non-traditional or nature-inspired or bio-inspired algorithms, and ultimately go and do all these things. I'm going to show you a simple application of how I use these algorithms to one of the real-life problem and try to solve these particular cases. I already briefly discussed to you about how the importance of reservoirs are there, the water requirement is there. We all know there is a tremendous pressure because of the increasing growth of the population. Food production also has to go up. That is when it can kind of cater to whatever is required. Now, which also means the operation and management of irrigation systems are also under tremendous pressure to more efficiently kind of work together to ultimately maximize the benefit. So one of the reservoir which I actually worked as a part of my research work is Mahi Bajaj Sagar project. Okay, that is located in Rajasthan, more specifically a place called Banswara. So it is kind of adhering to two of the neighboring states, Madhya Pradesh and Gujarat, right? So if you briefly say, their main purpose was to cater to irrigation and also to hydropower generation if there is more water. These are the various crops which are actually grown in the command area. Now, these are all some of the various salient features of this particular project. They have an inter-sharing agreement between Gujarat and Madhya Pradesh, and they have an area where different crops need to be grown. Now, the larger problem here is I will need to understand the actual problem. I will need to maximize my annual net benefits and subject to maintaining these constraints, right? So here I will also have to keep in mind how much water is going to come into the reservoir, which is a very, very important thing for me to understand that particular capacity. So here the gross storage capacity is around 2180 million meter cube, right? So if I kind of briefly understand what is actually happening here is, so the main tributary for this particular major reservoir is called the Mahi River, which is shown in this blue color. Okay. And here it comes in from Madhya Pradesh, moves all along Rajasthan, then moves to Gujarat. That is the way in which the river is flowing. So what they have done is, because of the natural landscape of how it is, the water gets stored here, right? And then it kind of goes to some part here in, there is one canal called Bungra Canal. And here there is a balancing reservoir. From there, usually for many reservoirs, you'll always have a left main canal and a right main canal, right? And there are two powerhouses. The main dam is here. There is one powerhouse 1 here. Powerhouse 2 is here before it kind of is released to Gujarat. Okay. That's what briefly is how this is there. And this is briefly the index map of this particular project. So because of the natural depression, this is the upstream side of the reservoir. And this one is on the upstream side. Once again, this was a picture which I took somewhere around lean month time where the water was low. This is simply the powerhouse 1 where the water gets to, and this was the balancing reservoir from where the water is going to go. This is here, the right main canal and the left main canal where water keeps flowing to subsequently the agricultural fields for farming. Now, what is the most important thing here that we are going to actually model? This is all there. I will need to decide at which month how much water will have to be released to these agricultural fields. That is reservoir release policy, which we will have to decide what is the most ideal reservoir release policy to make sure that there is going to be maximum benefit for all the farmers in this particular command area, so that they have highest crop yield capacity from their farmlands, and ultimately their economic levels and well-beings are going to get better, which subsequently is going to directly benefit for higher food production and overall economic well-being of the area and the state and the nation, right? So how do we do this mathematically is what I'm going to show you right now, right? So as I told you initially, whenever you think of a mathematical model, there are 3 major components. One is the design variable. Second one is what should be the objective function. And the third thing is what should be the constraints. Okay. So here, when I think of something like this, the first thing is about design variables or the decision variables. Now, as I told you, which crop should be actually grown is one thing that we will have to decide. Okay, that is usually there, that is already given in the database. Now, how much area of each crop should be grown in the command area? Now, there is a division. You have an LMC or left main canal. You have a right main canal. You have a Bungra canal. We did already see that there are actually 12 crops. All the 12 crops can be grown at any of these command areas is what was presumed, okay, based on the discussion with the officials. And the agricultural officers, based on the soil health and how well they can be sown, and there were caps given on whatever is the minimum requirement for that area for food production. And we said that this is something that we will tell the model to decide on its own how much is the area that we will have to grow, right? Then we will kind of decide how it is going to be appropriate. So this in itself, 12 crops for each of these canals amounting to 36 variables. Then subsequently, how much is the reservoir storage that we will have to maintain in each month? So when I say the storage in the month of January, I will refer it as S1 and so on and so forth. If I say S12, the storage in the month of December. And in some of these monsoon months, there is a possibility if there is heavy rainfall, beyond the storage, the water will have to overflow. So I would, given a choice, would want to keep this as minimal as possible whenever I do my irrigation planning. But still, I will need to keep them as variables of O1 to O12, right? And same way, my first priority is always with respect to irrigation for agriculture. So post that, I will try to meet the requirements for powerhouse 1 also, right? And here it's powerhouse 1, January, February till December. Their requirements are 12 variables. Then there is a irrigation demand, which means I am doing this as a monthly analysis. So in a given month, how much water is required for each canal, so that I decide and accordingly release so much water in, say, January, February, March, so on and so forth till December. Because I have 3 canals, so I have 36 different variables separately. And we also see, as an usual instance, when we go around all these particular command areas, people don't always only rely upon only this particular variables, right? They also go in with respect to the variables which are actual or groundwater withdrawal is also something that we commonly see. But given a choice, the government would preferably want to provide surface water for the farmers as a first choice for free, and they don't want them to invest anything extra if water is available from the reservoir. Those who are not able to get that from the projects only will be tapping these groundwater withdrawals, is what is the intention with which how this planning was made. So in January till December, how much groundwater is also withdrawn, keeping in mind the overall capacity of the aquifer potential in each of these areas was also considered as variables, right? So when I thought into all these particular things, these were all the variables. So now I will have to go into the second component of the model. What's my second component of the model? My second component of the model is I need to define the objective function. So I told you the objective function is, in a given year, what's going to be my net benefits that I am going to get in the process of coming up with an optimal reservoir release policy. Okay, optimal irrigation planning. So when a farmer grows so much of a crop, okay, so much area of a particular crop, usually government has some prices, which means how much is the net return from, say, a paddy or a maize or a sugarcane. All these things are kind of very clearly documented that is going to be there. So there is a benefit, net benefit, that's what it says, net return from a particular crop is a well documented thing from the agricultural department. Then I am actually keeping the variables, 36 variables, how much area of each crop I am going to grow in each of this command area for under each canal is also given. So based on the value, it will compute how much is going to be the benefit, right? So when I say net return takes care of all the other extra expenditure that I'm going to do in addition to the actual market price, what I'm going to get the benefit, minus whatever I have used the labor or the fertilizer or any other cost that I have incurred for ultimately growing the crop to the final stage. Now, in all these things, one more important thing which usually we take care is we always learn the concept of determining how a crop will ultimately come to its maximum yield capacity in the overall stage, right? we use the concept of a crop water requirement calculation using a method called Penman-Montieth method based on the meteorological data of that particular region. We can actually scientifically calculate for a particular crop, say a maize or a paddy, from its initial stage till the final stage, there is a crop coefficient, and how much water is required for it to ultimately grow there is also something that we can very scientifically calculate, and based upon how much area is there, we can identify how much will be the demand for that particular field as well, so that we don't unnecessarily waste so much water, and we scientifically also kind of segregate and divide the release of this particular water. Now, the other additional thing is, in order to discourage people in using the groundwater, so what I kind of added one more term is I am subtracting how much is the total water, groundwater that was withdrawn from that command area by multiplying it with some kind of a large groundwater withdrawal cost. Okay, which means if I reduce my benefit by subtracting this term, I would ideally want the model to push it in such a way that my overall groundwater withdrawals are going to be lower, right? So while I do this, what are some of the general conditions that I will have to keep in mind while I do this? I will have to keep in mind that my reservoir storage, say in the month of February, should be equal to what was the reservoir storage in the month of January, plus what was the water inflow in the month of January, then how much water I released for Bungra Canal, how much water I released for Powerhouse 1. There must be some evaporation losses, which is usually relative to the meteorological data or the temperature and all those things, which is very well recorded, and the surface area of how much water is there. Then if there are any upstream requirements, which I will have to send it to Madhya Pradesh based on the interstate agreement for this particular project. Okay, so this I will kind of write it for all the 12 months and make sure my water balance equation or the continuity equation is going to be very well maintained. Same, I have one more balancing reservoir. Here also the same way, this is also taken care. Now there are also command area limitations. What does it actually say? Usually there are different seasons, which means there is a Kharif season, Rabi season, and so on and so forth. So I'm going to limit the area of a particular crop only to so much, which means if there is a crop which is highly beneficial, my model should not blindly go and if paddy is the one that everybody wants to sow, everyone cannot do this. The government will cap and limit, only so much can happen, right? So that is kind of going to be taken with some of these limitations. And same way, this is going to kind of tell me, I will identify the demand based on how much area of a particular crop is there. I told you the crop water requirements I will calculate using one of the most popular methods called the Penman-Montieth method. And then I will decide what is going to be the irrigation demand for the left main canal, right main canal, and Bungra canal. And then for the canals also, as I showed you in the picture, there is a limitation. Only so much water can be distributed in a given day, and so much can be distributed ultimately in a given month. So my release cannot be beyond this particular capacity. So that is also going to be capped, and it should be only less than or equal to that particular value is to be kept in mind while I'm going to decide how much water is going to be released. Same is the case with respect to the water requirements for hydropower generation. There is a minimum requirement that has been kept in. Okay. Otherwise, if you want to make it as a multi-objective model, I can also say that maximize the benefit and maximize the hydropower. So whenever you kind of do this, now if I maximize the hydropower, my water requirement for irrigation might get reduced. So the benefits will have a trade-off. So I normally always have objective functions which are conflicting each other whenever I do these formulations, right? Some of the other things which I'll have to keep in mind is about the upstream requirements, then the evaporation losses. Then there are bounds with respect to what should be the minimum and maximum area of these crops. And the groundwater withdrawal overall cannot cross the total water that the aquifer in that particular area is going to hold. And also, I have a live storage, which means so much water only can be stored in the dam in a given month. I cannot cross that particular value also. Otherwise, that water is something that's going to overflow or I will not be able to use it, right? So this is what net in the shell of how I understood the overall model and brought in with respect to the overall formulation of this mathematical model, and it came down to be 120 variables and 93 constraints, right? So once I did this particular thing, I kind of assumed something. Usually for Indian scenarios, we don't kind of take the total water, because whenever I do the planning for subsequent years. So when I do it for next year or next 2 years from now, I will assume that the inflow, what I got in the historic period, say the last 30, 40 years, I'll use some statistical methods. And then if I have so much water, this is how I'm going to do the planning, right? So that's how we always do. So this is the part which I'm going to connect with the subsequent part of the talk, where I kind of took this particular input more precisely using artificial learning and machine learning methods, right? That's where is also a next extended research which I'm going to show on how I kind of used it. So here I use 75% dependable inflow scenario, which is usually taken for the planning problems for Indian conditions. And ultimately, I used one of the popular techniques on differential evolution, right? And then finally, what I got was, so this thing, what you kind of see, the total area under Kharif, Rabi, and all those things, the cropping pattern, what ideally should be there, which is going to give me 113.15 crores. Okay, that is what was the optimal cropping pattern which came in with respect to this particular aspect of what actually can be there. Then, if you kind of go, how is actually the release policy that is going to be? So this is something what I'm showing is, I fed this particular model into one of the optimization methods, and that algorithm finally gave me this as a final output. And I'm only showing you the final optimal solution of the formulated model, which I will kind of recommend it to the chief engineer of the respective project. If you run your reservoir like this, which means in the month of January, in each of these particular canals, if you kind of operate. So I can also do this on a daily basis as well. This is on a comprehensive macro level for monthly basis. If this is how you do the release policy, and this is the minimum groundwater withdrawal that you can possibly take in. So you will arrive at this particular thing of at least 113 crores every year is the net benefits that we are actually going to gain, which means we, in the sense, the farmers are going to get in from this particular release policy. Okay, so that is the first part of the talk for this particular case. Okay, so anyone has any questions on this particular aspect of the overall systems approach used on reservoir optimization? So I'll give a small pause. If anybody has any questions, I will be happy to respond to any of these things. Yes, please.
Sir. Yes, sir. Sir, there is 113.15 crores, whatever you told.
Yeah.
It was your calculation after applying A and ML to the system.
Correct.
Am I right, sir? So
You're
before applying, how much was
Yes.
the net benefit, sir?
So usually these numbers, we don't have it directly. So because the area, how much they are actually showing and all those things, they will not be actually having. So generally, their numbers will be relatively lower, because in some cases, if you kind of go into the command area. So in one of the recent studies where when I'm in Hyderabad, I'm going to show you the next one where we are actually working on Sriram Sagar project. So where we at least saw around 25 to 30% jump when they kind of go into a scheme, whatever we are showing is what you will see in the increase in the net benefit. For this particular project, we did not have the access to how much area is actually grown for that particular thing. So we tried using remote sensing data and then tried to do this particular thing for another project later.
Okay. Basically, some rough estimates, sir.
That's what I said. Usually, you can easily see around 25% jump from what is being done on the ground to what this particular optimal solution can actually increase to. 25% lower than this is what I'm sure it will be there.
Oh, very good. Oh, then
Yeah.
that is a large.
That's a reasonably good number,
amount.
mainly because what we always see on the ground, if you go, you will see that people don't have efficient water management practices. So if you kind of go in with respect to the calculation of what we always teach our students with respect to crop water requirement estimation. But if you kind of see there, the water kind of goes usually in the head. The usage of water will be very high. The tail people will always be suffering. That's also a scenario which we will normally see. These all, if better regulated and administered, we can definitely have a better planning and management for these particular cases.
Can the A and ML can also be applied to the implementation of your optimization techniques, sir?
Yes, definitely. So there also the other part, next to consequent thing in the reservoir optimization, one part where I have used these ML techniques largely, which I told you was with respect to the main factor for all these things, if you actually see, is how much water is going to be available for the reservoir, because the government always plans in future, right? So when the government plans in future, they will need to know a little more accurate figure, because there's a lot of uncertainty with respect to how the climate is actually there. So the prediction using these ML techniques were far better in comparison with the classical. I would say usually we use the variable distribution. So that's what we go by, using the historic data and predict for the future, right? So that's also a very important thing that we will be seeing in the subsequent part of my talk.
Okay, sir. Last question, if you allow me to ask you.
Please.
Yeah. So this 113.15 was the current thing. Going further, can it be another 25 to 30% increment?
So here, once again, this is linked with respect to how much water is going to be available. So this is the maximum. So when you get an optimal solution with whatever model formulated we have done, you will not be able to get anything better than this. So
yeah,
this is
yeah. Oh, go ahead, sir.
This is very much related to the mathematics of the curves, which I told you. It's a maximum point on the curve. Unless and until some condition on the ground is going to change, you can't get a better value than this.
But a lot of your calculations are all based on the ground level data available now, sir.
Yes. So this is the best you can get for this.
So obviously your study and your results, whatever you got, are all based on the available data. The actual data is at least
exactly
80% to 90%. Am I right, sir?
Correct.
So obviously it is not now nothing. You are not leaving anything unknown. You have captured that the number of variables that you have captured and number of constraints that you have taken into picture are all been capturing whatever the available natural, physically available data. Am I right, sir?
Yes.
So
agreed. There are a lot of uncertain things which we assume. So first thing which I told you was with respect to the inflow availability. So we are assuming 75% water of what is available as per the calculation based on the historic last 30-40 years of data is what we are assuming. That is a little uncertain. And the second thing which we also would assume is when I start actually, I can say releasing 1 unit of water, I am assuming that only 50% of the water will be going and reaching the farmer. So there is a 50% conveyance loss because it's all open channel and many things are not very well maintained. So that's also an assumption. If these all things are going to change on the ground, the overall output of these things can subsequently increase also.
That is well understood, sir. But the major thing is that approximately
Yes. Yes. Yes.
the approximate variance may be only to 10 to 15%. Uncertainty, what you're talking about,
Correct.
is only
Correct.
to 10 to 15% of whatever you have calculated.
Maximum.
So that is not a major concern when you are doing so systematically.
Yes.
So that uncertainty is only some maximum. It should be go on and decreasing up to 10 to 15%, if I am
I
right.
agree.
Yeah.
Yes. Yes. Very much.
So let's not talk about uncertainty at all, because there is a very systematic approach you have done. That
Yes.
uncertainty is only 10 to 15%. Let us not talk about that at all. So coming into picture, going further, this 113.15 should be at least theoretically increased by another 25% or 30%. Am I right, sir?
So this is an optimal value. So beyond this, at the maximum, as you rightly said, it can go to only 10% more, not more than that. So
No,
this is
earlier it was 25% increase, no, sir? Approximately, at least.
I said the earlier number, if you see what is on the ground, it will be 25% lower than what this is right now.
Correct, sir. So this 113.15 is 25% approximately, at least, than what it was, what is ground reality.
Yes.
Now going
Yes.
further, this 113.15 should increase by another 20%. Am I right, sir? I'm just trying to theoretically, I'm telling.
Unless and until whatever assumptions we have taken in the model changes, it won't change much.
That's true, sir. Again, we are talking about the same thing. The uncertainties again is basically some 10%.
Correct.
Yeah.
That's all.
So okay.
It is always supply demand, right? As simple as that.
Yeah, that is true. That is all agreed, sir. That is all. It's a it's a very normal logic. But very nice presentation you have been doing. So that I'm just trying to extrapolate and try to tell to these government agencies, we make, I mean, everything is very streamlined. 13.15 is will obviously go to another 20% extra.
Correct.
With all uncertainties, percentages, and things like that.
Yes.
It's only that implementation.
I agree.
Very nice.
Many consultants usually kind of do these background studies and submit the report in detail to the government using exactly the same process before they make decisions.
Fine, sir. But they may be doing with all the available techniques, but this A and ML techniques, I think will be much more beneficial.
Yes. Things will keep getting better with the available techniques as well.
Thank you, sir. Thank you, sir. Thank you for
so I will move on to the next part as well. Right? Any other questions from anyone? Okay. So I think because of an interest of time, I will move on to the next part of my talk. So this is where I specifically wanted to emphasize a little more in detail, where you kind of see that I specifically told you one of the important thing about the future inflow predictions. Now, when I say future inflow, I told you that that is one of the very important input, because that's the basis on which how the entire planning and management happens. So while traditionally we use a variable approach, a statistical method that we have been doing, and we go by the 75% dependability, because a lot of things change when this number is going to change with respect to the overall scenario. And also a very important thing which we wanted to do a study was, how do I think of a long-term scenario? When I say long-term, how do I see it in 2050 or 2075 or 2100? Using some of these climate change scenarios, what is actually going to change? So we tried doing a brief analysis with respect to how this is going to, this particular research work actually was trying to examine some of the very well-known methods. So usually the LSTM method, if you kind of see, I'm assuming that the earlier speakers would have actually talked to you about various techniques. At least from my background research, there are some methods which I have personally got benefited, and I will always say for people who are beginning the research could start off with that at the end. So here in this particular research, the LSTM method, one of the deep learning technique, has been doing very well in many applications. So where we added additional thing of attention mechanism, where the term that is actually LSAM, and the boosting techniques are also someone that is actually doing very well in the history. So we also use this natural grading boosting technique in predicting the monthly inflow for one of the major reservoir projects, Sriram Sagar project, here specifically in Telangana, India, right? So that particular study is what we kind of carried out. So when we tried to do this, we wanted to predict the reservoir inflows from the climate change perspective, as I told, in short, mid and long pathways. So there, how exactly these particular annual inflows are changing is a study that we tried to do, right? So we all know, as I told you, these inflow predictions are very, very essential in effective decision making, right? So that is something that we will need to understand in this particular aspect of it. So this is where, very briefly, the what I call a Sriram Sagar project, in short as SRSP, the catchment area is pretty much there in Telangana, right? So this is briefly the workflow of the study, what I actually did. I'm going to briefly take you through the process, okay? So that I'll at least keep last 5 to 7 minutes for some kind of a discussion. So what I did was, I had historic data, okay, monthly historic data from 1983 to 2024, right? So what are the historic data that I had was rainfall, okay, the maximum temperature, minimum temperature. And usually what we have also seen historically is future prediction of rainfall is very, very challenging even today with whatever techniques you have. Researchers still cannot reach to the extent of a higher level of accuracy. We are extensively working on that, but without this particular thing, we will still not be able to go with a far more better prediction. That's where we thought that because all these ML techniques are doing wonderfully well in many of the applications, let us try to analyze and explore this study. So when you kind of do it, we are doing a prediction, like you need to do a forecasting. So what could be the different input scenarios when we wanted to explore? So that's where we tried dividing them into multiple scenarios. So for scenario one, we took the, you can say the rainfall, okay, which is the current month, okay. And similarly for the discharge of the previous month, that was one thing as an input. Same way, the rainfall of that month and the previous month. Then the discharge, sorry, here the discharge is also there. So that is also something that we took. Here, once again, we took here, if you see, 4 inputs. So we took this data, okay, overall data, what we have, we divided them into 70 and 30. And usually what we have seen from the literature is they do reasonably well when you have a 70-30 split, which means for training, we take 70% of the data. And for testing, we take 30% of the data. So naturally, we'll have to do some kind of a normalization. Then we tried doing some combination. So there, I did not specifically mention too much about the particle swarm optimization, and here GS is called the grid search. So here I was trying to use these optimization techniques more specifically because there are a lot of user-defined parameters in machine learning algorithms. So if you correctly kind of have the values for these particular things, hyperparameter tuning will significantly influence how the performance of all these particular things are going to do very well. Okay. So that's where we were kind of wanting to use these PSO and grid search, which we call in short as GS, to actually use them to do the hyperparameter tuning for these algorithms and kind of see for each of these scenarios, which one is ultimately going to be relatively do a better prediction in terms of the future reservoir inflows in the short, mid, and long term. That was our primary intent in this particular process, as you kind of see. Then we also have something called as a denormalization, which we usually do, right, in this particular case. And I'm not going to spend too much time. So this is a database technique where we kind of make sure that it's going to be far more better. And ultimately, we are going to use the correct scenario, and we are going to have 4 different evaluation metrics, which we have actually used in the paper to compare which one is doing well, and finally arrive at this particular input data and the inflow predictions. So if you kind of go very briefly, the statistical information of the input variables that you see, we did do a lot of analysis with respect to the mean, kurtosis, skewness, and all these things to understand how complex this particular data is there, right? And here, based upon this particular kind of analysis, as I told you, this was for 42 years, from 1983 to 2024, right? So that is what was available from the irrigation department, what we took. So here, if you see the training period, we took from June 83 to December 2011, around 343 data sets. And testing period is around 149 data sets. So one thing that you must have heard from the earlier speakers also over the last few days is larger the data set, more accurate these all algorithms will actually be better able to train and give a better relationship between the input and the output variable, right? So this was the best number of data sets that we could actually have to actually do the training for them to understand between the inputs and the output. Okay, so that part was actually done. So then what we did was we tried analyzing them using all these particular algorithms. Okay, so this was the observed data, and these were the subsequent data which is actually there from all these particular instances of these ML combinations. So what we actually saw was this figure is revealing that during the training, this part is for the training and this part is for the testing. So what we actually see in this particular case is that they are capturing the variability more precisely with respect to more specifically of this NGB based all these combinations, right? And in the testing cases, what you actually see, the observed inflows are actually displaying a skewed observation across these particular things, because ultimately a larger importance is usually given for the testing phase, because this is known data, this is unknown scenarios, right? So here, this LSAM PSO provides the closest match to both the central tendencies and the extremes, okay? That is what, if you kind of see the observations are there with respect to all these scenarios. I'm not getting into the details of the analysis. So this is also one more thing which we did with respect to the performance of all these particular results that you actually see. So what you actually see from this particular result. So when you see here from this particular figure, what we are actually seeing, you clearly see is the scatter plot between the observed versus the predicted inflows, right? So here there is a closely distributed scatter points that are around this 1:1 line, which significantly is predicting a general consistency with the observed values. Okay, so there are no points lying drastically very far away from the 1:1 line, which also is confirming to the robustness of the predictions, and it is not kind of having major prediction anomalies. There will be there, but relatively this is okay. In the training phase also, you see that the alignment is reasonably strong. So that part is there. And in the other case also, you kind of see that the testing phase also, you will see that things are relatively okay. But more specifically, what you see that here is the LSAM approach the LSTM AM approach using this hyperparameter tuning with the particle swarm optimization part is actually doing reasonably well in the prediction of all these inflows. Okay, that is what you kind of see. So more specifically, if you have to see, we actually took this future data from 2025 to 2100 using 13 downscale GCMs under 4 SSPs. Okay, and an average of these ensembled values from rainfall and temperature was computed, right? And we largely took for scenario 3, where it reasonably did very well for the various performance metrics that we actually see. So because of paucity of time, I'm just telling you how these techniques were actually used very well. People are welcome to look at the paper of ours, which will have in detail all these particular analysis and explained more detailedly how exactly these particular methods are doing very well, right? So here, if you kind of go in here also, if you see that for short, mid and long, okay, for the maximum inflow, if you kind of see here, you saw that the maximum inflow here for this particular case of these scenarios is 1196 million meter cube is what you actually see for Sriram Sagar project. And if you kind of compare it with respect to average, which will kind of give you, this is how typically it has been there. Now in the long term, when you kind of see these things are also varying depending upon the kind of scenario which we kind of project and foresee for the futuristic aspects of how things are going to be there also. This is also some kind of specific values which kind of gave in. Now this will be far more, I can say, predictable and more accurate in comparison with the classical statistical techniques if we had actually used, where we cannot even predict to this extent and they will be giving very different results. And this were kind of giving far more better with all the statistical techniques and tools that we were actually going to use in these particular scenarios of how exactly we are kind of going to use in these particular scenarios, right? So once again, when you kind of see the solutions of such challenges in these kind of projects, usually when you go discuss with the chief engineer, they will always say they have several other challenges. Like they have desilting issues, they have how do they actually preserve the current reservoir storage capacity and all those things. In addition, with time, they will also keep changing with respect to putting many balancing reservoirs like the mid-Menar, lower Menar, those who are actually aware of this project during the flood period and all those things. While we keep all these particular things, we need to keep in mind that whenever we are going to do these kind of the significance of all these machine learning techniques in these predictions, right? The annual flows for these particular kind of scenarios or wherever you do prediction or forecasting, what I can broadly say is these have actually done reasonably well, and these LSTM methods have comparably done very, very well with respect to all these scenarios. So that is what briefly I would like to say in the application of these particular cases. Now, in addition to this, this is something that you all would have actually gone through in several aspects of this. What I will kind of focus very quickly on the next 2 slides and converge and open up the floor for some general discussions is how things have evolved over the last 15 years. So this part, if you kind of see, people have started off with the statistical era from 2010 to 13, then various algorithms like random forest, gradient boosting, ADA boost, and all these things were all there. And the ensembling learning was actually taking over till 16. Then these deep learning things like the CNN and LSTM and RNN kind of took over. And off late, if you kind of see the various, so this XG boost, all these boosting methods have been doing exceptionally well with the use of all these optimization things for the hyperparameter tuning. Now today, the other thing which is also doing very well is this physics-informed AI techniques, right? How you actually interpret the data with what is actually happening and kind of use it for these particular things is today's scenario. So for people who are beginners I would suggest you to start with these algorithms, right? Then if you want to go with better ones, go with boosting algorithms. And people who are wanting to do research and who are into those particular aspects, this is what is the order. This is where you will ultimately have to go, kind of tie up with all these sensors where real data actually comes in. You can develop digital twins and ultimately keep using them to keep churning this feedback model. And the real time monitoring is what is going to be the order. And this is where most people are actually working on in using for the resilient infrastructure design, right? While you do this, as a closing remark, what I'll kind of say is it's very, very important. Don't blindly assume that these all are going to do excellent. Okay. There are so many things that you will have to keep in mind. Without all these checks and balances, you cannot blindly go and assume AI is powerful, but responsible engineering in making sure when, what kind of data you need to do validation and you have to interpret these results. That is when you can rely on the results, which we will assume it's going to be accurate. Okay. You will need to document these assumptions and limitations and keep reviewing it. And the quality of data is very, very important for us to meaningfully interpret these particular things, right? It will only aid you. It cannot replace you is something that we'll always have to believe, right? So that's what is this in a brief nutshell. With this, I come to the end of my presentation. Thank you very much for patiently listening. Now I open the floor for any general discussion to the audience. Thank you.
Thank you, sir.
Yes, sir.
Yes, sir. Sir, this was a fantastic work you have done, sir. I think for the human thing, in Subhashitani, they'll tell Annam Jalam Subhashitam. So you have concentrating on Annam and Jalam. It's a very good thing. My request is that if at all you can hands-on session, you have told, if you can share with us, we will also go as a homework. We will also do that. And I request all the organizing committee to organize one hands-on session so that we can also. I think there will be a lot of work to do, no, sir, further going. So we will
yes,
also.
yes. As you rightly said, usually whenever we also conduct such sessions, when we do this, at least 50% of the session, we always encourage learning by doing. That is the way to go, and that gets more interesting, more active participation also is there. When there is an opportunity, we can always explore that possibility, and I will share the link of my paper with the organizers, and they are welcome to share it with all the participants.
Sure, sir.
Yeah.
Thank you. Thank you very much, sir. Very nice of you, sir. Thank you very, very
Thank
much.
you. Anyone else? Any other questions? Okay.
Right.
Sir, if there are no questions, shall I ask you another question, sir, if you don't mind?
Yeah, please.
Sir, is linking. Yeah. If there are no
Sir,
other. Okay.
due to shortage of time, can you mail us, sir? The questions we will get back to you by contact.
Kindly send the mail ID, madam.
Sure,
If you don't mind.
Sure, sir. Sure, sir. Due to time constraint, we are not able to go. Thank you, sir. Thank you, Dr. Vasan Arunachalam, sir, for your highly insightful and engaging session. Your talk on integrating machine learning with particle swarm optimization for enhancing future reservoir inflow predictions has given us a deeper understanding of how advanced computational techniques can significantly improve the accuracy of hydrological forecasting. The way you explained the integration of machine learning models with particle swarm optimization was both clear and thought provoking. We especially appreciate your emphasis on optimization model parameters to achieve better prediction performance, which is crucial for effective water resource management and planning. Discussion on handling uncertainty in inflow predictions and the importance of reliable data for building robust model were very enlightening, sir. The session has truly highlighted how such innovative approaches can contribute to the sustainable reservoir management and help in making informed decisions in face of challenging climatic conditions. Thank you once again, sir, for sharing your valuable knowledge and expertise with us. Thank you, sir.
Thank you. It was my pleasure. Thank you.
I request one or two participants to unmute yourself and give a feedback for overall FDP for 1 or 2 minutes. You can unmute and speak a few words. Okay. Now I request Dr. Ravikumar H, Head of the Department, to give concluding remarks. Sir, over to you.
A very good afternoon to one and all who are present here. It gives me an immense pleasure to deliver the concluding remarks for the 1-week faculty development program on AI and machine learning application in civil engineering. Over these past 5 days, we have witnessed an enriching journey where traditional civil engineering practices met the transformative power of artificial intelligence and machine learning. The sessions have spanned diverse domains: structural engineering, geotechnical engineering, pavement engineering, and finally, we ended up with an water resources, highlighting how data-driven approaches are shaping the future of our field. I sincerely hope that this faculty development program not only has enhanced your technical knowledge, but also inspired you to explore innovative research directions and integrate AI and machine learning tools into teaching and professional practice. I would like to express my heartfelt gratitude to all the distinguished resource persons for their insightful lectures, valuable time, and willingness to share your expertise, and your contribution have been very, very instrumental in making this program a success. I extend my thanks to all the participants for your active involvement, thoughtful interactions at the right time, and enthusiasm throughout the program. Your engagement has truly elevated the quality of the discussions for this faculty development program. My appreciation goes to the organizing team for their meticulous planning and seamless execution of the event. This faculty development program aligns with our broader vision of promoting quality education, fostering innovation, and contributing to the sustainable infrastructure development, echoing the goals of academic excellence and societal impact. As we conclude, I encourage all of you to carry forward the knowledge gained here and apply it meaningfully in your teaching, research, and professional endeavors. Thank you once again for your active participation and support. I wish you all the very best in your future pursuits. Thank you.
Thank you, sir, for your guidance and support in successful conduction of this FDP. Now I request all the participants to switch on video. Just we'll take one group photo here itself. Watson, sir? This only, no? Shall I I'll take this. Thank you, everyone.
Thank you, madam. Thank you.
Thank you. Now I request Professor KVR Prasad sir, Associate Professor, to deliver vote of thanks. Over to you, sir.
Good afternoon to one and all. I, KVR Prasad, Associate Professor, Department of Civil Engineering, SRMBIT, is privileged to present the vote of thanks of today's program. First of all, I take this opportunity to thank Dr. Vasan Arunachalam, Professor and Dean, Administration, BITS Pilani, Hyderabad. Sir, we are thankful to you for making your time and sharing your valuable inputs and expertise to our participants. Thank you, sir. On behalf of the Department of Civil Engineering, SRMBIT, we thank our management and our secretary, Sri Sanjay K.R., our academic committee chairman, Sri K.V. Sekhar Raju, sir, of our Sri Krishnadevara Educational Trust, Bangalore, for permitting and supporting us for the conduct of this program. I thank our principal, Dr. M.N. Tippeswamy, and our vice principal, Dr. Bharati Ganesh ma'am, for their support and guidance for the successful conduct of this program. I take this opportunity to thank our head of the department, Dr. Ravi Kumar H., for his continuous support, guidance, and time-to-time inputs throughout the conduct of this program. I thank all our faculty coordinators and our media publicity team for providing the YouTube link for the participants to join and to witness this program. So, who are all instrumental for the successful conduct of this program, we thank every one of them. We also thank our resource persons, Dr. M.A. Jairam from Rasta, Bangalore, Dr. Kushbu A. Jain, IIIT Nagpur, Dr. Jaikesh, NIT Arunachal Pradesh, Dr. Chandru Bogireddy, Tajikistan, Dr. Vasan Arunachalam from BITS Pilani for sharing their valuable inputs and expertise, knowledge with all our participants. Last but not the least, we want to thank all our participants who were there nearly around 150 in number from various parts of India for their continuous support, for patient listening, and also we thank Professor Jairam, who was always interacting with the speakers for asking enthusiastic questions and for his interaction. We thank each one of you who helped us for the successful conduct of this program. Hopefully, with all of your cooperation, we will try to conduct some more programs of this kind in future also. Thank you one and all. Have a good day. Over to you, ma'am.
Thank you, sir, for a brief vote of thanks. A feedback link is shared in the chat box. Please fill it.
Yes, sorry, Mr. Thank you.
Dear participants, please fill the feedback which is there in the chat box. You will receive the certificate within 2 days. Thank you. Dear participants, if you have any queries regarding any sessions of this FDP, please mail it to us through hod_civil@sarmbit.edu, which is there in the chat box. We will get back to you with the answers. Thank you.
you